Okay. So last time we were discussing uniform metric before my laptop's battery die out. Uniform metric was the following metric on the set of bounded functions on a non-empty set. So let S be a such set, non-empty set. We know what's the bounded function. So if the values of the function is bounded by two real numbers, minus m and big M, then we call it bounded. Then we consider the set of all bounded functions, and on this set we define the following metric, Supremo metric, as follows. Given two functions, we define the distance between these two functions as the supremum of this expression. Since f and g are both bounded, this difference is bounded, and therefore the absolute value of this distance is bounded, and we just take the supremum. Okay, so let's show that this is really a metric, and maybe before that, let me describe this on. Okay, first let me prove that this is a metric. So, do you have any questions so far? So our claim is that so this soup is a metric. On BS. Proof is the following. First, we need to show that actually this supremum really exists. So this is a bounded set, but that's easy. Since f and g are bounded, since f and g are bounded, say by m1 and m2, we have what? The following. F of s is always less than, let's say, m1 and greater than minus m1, and g of s is greater than m2 and less than m2 for all s in s. But then you see, then minus g will be between minus m2 and m2, right? So then if you multiply with minus 1, you get, or maybe I should say the following. See, then f of s minus g of s what is this? This will be, maybe I should, okay, f of s g of s. This is always larger than minus. Okay, maybe I just write this. Then what is f of s minus g of s? The biggest value g of s can take, right? I can write this f of s plus minus g of s, and minus g of s is larger than, right, minus m2 and less than m2 again. So the sum of these two functions will be less than, this is less than m1, minus g of s is less than m2, so this is less than m1 plus m2, and f of s1 is larger than minus m1, and this is larger than minus m2, so the sum will be larger than the sum of these two, so that absolute value of f of s minus g of s will be less than m1 plus m2, right? Because it is between this number and it's negative for all s. In particular, this expression is bounded, hence d sup fg, which is the supremum of all these differences, this exists, okay? Then we have to do what? We have to show that d sup satisfies the three axioms. What were they? The first axiom, positivity. D sup should be positive. Well, D sup is the supremum of non-negative numbers, right? These are all non-negative. Therefore, supremum is positive since each f of s minus g of s is at least 0. Moreover, if d sup fg is 0, this means what? Well, all these numbers are non-negative, so they are at least 0, but the supremum is 0 means, there is no positive one, right? D sup is 0 means then we have this. These are all larger than 0, but their supremum is 0, so that 0 is also open bound, is an upper bound, and thus f of s, right, this is 0, is equal to g of s for all s. Well, if two functions are equal to each other for all s, we see that hence f equals g, right? These functions are the same. So this is the positivity axiom. What about the symmetry axiom? Well, this is easy. Why is that? D sub fg. What is this? This is supremum of f of s minus g of s, right? S is in s. But clearly I can replace this by g of s minus f of s because absolute values of these two expressions are the same. But by definition, this is just d sub of g and f. Okay. All right. What else? We have transitivity. No, triangle inequality. Okay, so let f, g, and h be bounded functions. Okay. Then we have this f of s. Then for any s in s, I have this f of s minus h of s is less than what? This is okay. This is equal to f of s minus g of s plus g of s minus h of s. And I apply triangle inequality to this sum. So I write this. And what is this? Of course, this is just one of the expressions, one of the terms in this set. Therefore, this thing is less than the supremum of this set, which is d sub fg, right? Because d sub is the supremum of such terms. And similarly, this is less than d sub of gnh. But what we have seen is the following. For any s, this expression is less than this real number, right? This is a real number. Hence, d sub fg plus d sub gh is an upper bound for which set? For the following set. F of s minus h of s in absolute value, s is in s. Right? So this real number is an upper bound for this set. In particular, this will be larger than the supremum of this gadget. Hence, supremum of this d sub fh, which is the supremum of this set, is less than the upper bound. And this finishes the proof. Okay. Any questions so far? Okay. Let me maybe illustrate this on a picture. What kind of object is this? For example, let me give this example. S to be R. Okay. Then BS is what? BS, which is BR. This is the set of all bounded functions from R to R. Okay, bounded functions. And what is the difference? What is the sub metric here? You see, let's take two bounded functions. One of them is, let's say, this one, and the other one is this. Right? So this is y equals f of s. This is the y-axis. This is the s-axis. This is y equals g of s. What does this metric doing is the following. You see, for any s, sorry, for any s, I look at f of s and g of s. I measure this distance, right? And here, let's say s prime. So this is f of s prime, g of s prime. Right? I look at these distances and take their supremum. So d sub f and g is the supremum of such distances. I'll measure the distance for each s and then take their supremum. Okay, so this kind of measures the distance between the two graphs, right? Graph of f and graph of g. It is always good to keep, pictures like this in mind. Okay. Any question so far? Neyi indireyim? Sayfayı şey mi diyor? Yukarı mı çıkartayım? Şöyle mi? Tamam. Tamam. Tamam mı? Okay. Let me give another example. This will be also very useful. Let this time s to be n, the set of natural numbers. So you may start from 1 or 2 or 0 or 1. Okay, let me start this time from 1. Sometimes I start from 1, sometimes I start from 0. Doesn't matter. Okay, so what is BS is then? First of all, what's a function? A function from S to N, no, S to R is what? It's a function on the set of natural numbers. So it's a sequence, right? A function, şöyle yazayım. A function A from S, which is N to R, is just a sequence, right? Because it takes values on the positive integers, including 0, and the value of A at any n is denoted. So this is an, right? An by simply a sub n, right? Since we can count the positive integers, usually we describe a function on positive integers by just listing all the values, right? We just list the values and that's the function. And I can apply the above construction Supremo Metric to this example. So in this case, Bn will be what? Bn will be just sequences. An is a bounded sequence, right? A bounded function on the set of positive integers, including 0, is just the set of bounded sequences. And what is D submetric? D submetric for two sequences, distance between them is just the supremum of an minus bn. N is in n. Okay. We have a similar picture actually, but this time we have values only for integers. So let me again draw a picture. So this is the real numbers, but we have only in the domain integers. Maybe I choose. Yes, so we have positive integers actually. So I have 0, 1, 2, 3, 4. Okay. And our sequences are like this. Let's say maybe A1 is here. It's a bounded sequence. A2 is here. A3. So I am just drawing its A4. No. 2, 3, A4, and so on. This is A0, A1. Yes. And we have the sequence B. Let me use a different color. Maybe B0 is here. B1, B2 can be here, B3, and B4. So what we do, we just look at the distances between the values, differences between the values. So I measure this distance, I measure this distance, and then this distance, this one, and so on, right? And take the supremum of all these. Supremum exists again because we consider only bounded sequences. Okay, does it make sense? Do you have any questions? Okay. I have a definition. Now, let xt be a metric space. And y a non-empty subset of x. Okay, I have a metric space and a subset, non-empty subset. Then I may consider the metric function which is defined on x cross x as a function on y cross y, because y is a subset, right? I just restrict my function to y. Then yd is a metric space, is also a metric space because I didn't change the function d, right? These axioms are satisfied for all elements in x. Therefore, they are satisfied for all elements in y because y is a subset of x. Hence, this is a metric space called a subspace of xt. Okay, so I keep the metric, just change the subset. Okay, so this is the definition of subspace. Okay. As an example, we may, for example, consider the following. Let I be the 0, 1 interval. then bi, the set of bounded functions with the sub metric. So I consider bounded functions on the interval 0, 1. Then this is a metric space. This is the metric space of all bounded functions on the interval 0, 1. We know from calculus that we haven't seen continuity in this setting yet, but we know from calculus what's the real function, what's a continuous function on an interval on the set of real numbers. And we know that on a closed bounded interval like this, right, continuous functions are continuous. So recall, we will prove this later, but just now, take it as granted. Recall that a continuous function on I is bounded, right? Any continuous function on a closed interval has maximum and minimum. Thus, the set of all continuous functions Ci is contained in Bi, because any continuous function on a closed interval is bounded. Hence Ci, so I restrict my metric D sub to this subset, becomes a metric space. Okay, so I can just consider continuous functions with, again, the Supremo Metric, and this tuple is a metric space. Actually, it's the subspace of bounded functions on the interval I. Any questions? Of course, continuous functions are very important for us, and we will consider this metric space a lot. Okay, now we will define open and closed balls. Okay, so let XD be a metric space. Please stop me, whenever you don't understand anything. R, a positive real number, and X just a point. Now we define the following. Then the set B X R, which is defined as follows: the set of all elements in X such that the distance between x to y is less than r. Okay. This is called the open ball in xd with center x and radius r. Why is that? Well, we can draw a picture for this gadget. This is a symbolic picture, not necessarily in the real picture, because we have seen that, for example, uh, x and y can be functions, right? In the set of functions, we have supremo metric, so x and y could be functions, but symbolically, we can uh, draw such a picture. X is the center, and what I do, I look at all the points in x whose distance to x is less than r. So we kind of take the ball around. Okay, and here radius is just r, and y is a point here. Okay, so this is the open ball with center x and radius r. We could define closed ball. Similarly, for uh, r, this time uh, can be 0. The closed ball with center x and radius r is defined as, so we use in the notation this time brackets, the same definition basically, the set of all y's in x such that the distance from x to y, this time not necessarily less than x, we also allow equality. Distance from x to y is less than or equal to r. Okay, so pictorially this will be done like this. X is here, r is here, and y is any point. This time y can be somewhere here. Again, these are not real pictures, right? These are just some illustrations, but very helpful ones. Okay, we will always draw these pictures in understanding theorems, results, and also while we are proving some results, again we will use these pictures. Any questions? Let's see examples. First one is xd. Let's take the set of real numbers with the absolute value metric, right? Usual metric. Then what is a ball with radius r, open ball? Well, you see, this is by definition y in r such that the distance between x and y, dxy, is less than r. But what is dxy in this case? Well, I am using the absolute value metric, so this is just x minus y less than r. So what is this? This is just the set of all real numbers y in r so that the distance between x and y is less than r. So this is just x minus r and x plus r. This is just the open interval, right? And similarly, what is bxr? This is just, this time I will allow equality, so it will be x minus r, x plus r. Second example, let's take x to be r2 and d to be the d2 metric. So what is d? Let's say x1, x2, y1, y2. This is just the usual Euclidean metric. x1 minus y1 squared, x2 minus y2 squared. Hence, if let's say x is just x1, x2, then and let's say r is a positive real number, then what is the ball? bxr. Well, this is the set of all y's, which is y1, y2 in r2, so that the distance dx1, x2, y1, y2 is less than r. But what is this distance? So y1, y2 in r2, this is just x1 minus y1 squared, x2 minus y2 squared less than r, and this is nothing but x1 minus y1 squared, x2 minus y2 squared less than r squared. So this is just the usual, right? Usual ball. Let's say this is x1, this is x2, and I have a ball of radius r. Okay, r, and here is my point y1, y2. Okay, so this distance is less than the radius. So in this case, our pictures are the real pictures, right? Okay. Yeah, it is here. Center is contained in the ball. Because when you plug the center, you get x1 minus x1, which is 0 squared, x2 minus x2 squared, which is again 0, and that's less than r. Therefore, 0 is contained. Oh, you mean the radius, 0 radius? Well, if you take r to be 0, then you get, of course, all right, so you mean this. if R is 0, then in any metric space, x comma 0 is what? So this is the set of all x y's such that dxy is less than 0, right? But that is not possible because dxy is never negative, right? Therefore, this is just the empty set. Okay, so a ball, open ball with radius 0 is just the empty set. But okay, we may consider this. Yeah, you're right. So this is just a remark, maybe. Is this what you were asking? Yeah, yeah. Okay, yeah. You're right. You're right. Uh, let's continue our examples. Let's say, let's consider the Supremo Metric. Uh, so let's say S is 0, 1. Okay. And let's say uh, F is just the 0 function. Okay, any function. Any function. Bounded, of course, and R is a positive number. Let's see what is this ball. So R, what does this mean? This is the set of all functions, right? Bounded functions such that the supremo metric between f and g is less than R. But what is the definition of supremo metric? This is just supremum of f of s minus g of s, and okay, s is in s, so this thing is less than R. Okay, so pictorially this is something like this. Okay, here is the function f. Okay, so this is y equals, let's say, f of s, and I consider, so in the ball BFR we have functions, bounded functions, so that the distance from f to g is at most r units. Well, how can I do this? So for any s, the distance between f and g will be at most r. So the maximum amount I can go up or down from this point is r. So I can move up to this point or this point. This is, let's say, the distance r. Okay, and for each point on the graph I have the same thing. So we just have, something like this. I just kind of draw parallel copies of the graph. And what are the elements of this ball? They are the functions whose graph lies in this region. So a typical element of the ball is a function whose graph is, uh, in between these two red dashed curves. So this is g of s. Okay, so this ball with center r and radius center f and radius r is the set of all functions whose graph lies in this region. Okay, so this is a picture of a ball kind of in the Supremo Metric. Okay, let's see how much time do I have. Yeah, I still have some time. Okay, let me give you another example of a metric space. Uh, let X be any non-empty set, any non-empty set, and D be the function defined as. So D is a function. It will be a metric, and it is defined this way. Whenever you give me 2 points, I check whether they are the same point or not. If they are the same point, I say that this distance is 0 if x equals y. Otherwise, I say the distance is 1 unit. Okay. This function defines a metric on R, on X, and here X is any set, any non-empty set. I put this metric. Then claim D is a metric on X. Okay. So it has to satisfy the 3 axioms, right? M1, positivity. dxy should be always positive. Well, of course, it takes just 2 values, 0 or 1, for all xy in X, and dxy becomes 0. Well, let's see when this is 0. This is 0 only if x equals y, because if they are not equal, then it takes the value 1. So this is 0 if and only if x equals y. So the first axiom is satisfied. The second axiom is trivially satisfied, right? Because the definition is symmetric. You can replace x and y here. Nothing changes. Trivially. So for all xy in X, right? What about the triangle inequality? So let x, y, z in X. Then what about the distance between X and Z? You see, then note that if X and Z are different, these are different, then either X and Y are different, or Y and Z are different, right? Because if this was an equality and this was an equality, then Z would be, X would be equal to Z, right? So if these are not the same, an element cannot be equal to both of them, right? This means what? Hence, dxz. What is this? This is 0 if x is uh, equal to z, and 1 if x is different than z. But you see, if this is 1, in other words, if these are different, then either this holds or this holds. If this holds, then the distance between x and y is less than 1. And if this holds, then the distance between y and z is less than 1. In any case, one of them is 0. So this thing is less than. This is either 0 or 1. And if it is 1, then either this one is 1 or this one is 1. In any case, this, so, okay, maybe I should write like this. This is less than 1 and 1 if x is equals. This function is less than this function, and this function is less than dxy plus dyz. Maybe I should say this is the function 1, right? 1, and this is 1 is less than this because one of them is 1 and the other one is I don't care about the other one. One of them is 1, therefore the sum is always larger than or equal to 1. But this is just the triangle inequality, right? I have this expression is less than this sum. Hence, this is a metric. Hence, xd d is a metric on x called the discrete metric. We call the discrete metric because we define what it is. Okay, and it exists on any set. Okay. Okay, I already passed 3 minutes, so let me stop at this point. I will continue in a minute.